Hello students! We are going to cover Chapter 4, Electronics. From this topic, we will summarize the expected learning outcomes of Chapter 4, Electronics in the form of concept map. In this chapter, we will learn and understand more about electronics. There are 5 main sections in this chapter. First are cathode rays, second semiconductors, third diode, fourth transistor, and the last is logic gates. Today we are going to learn application of electronics, cathode ray oscilloscope, and semiconductor diode. Applications of electronics. Consumer electronics. Consumer electronics are devices and equipment meant for everyday use. For example, home appliances, audio and video systems, smart grid systems, advanced consumer device, and industrial automation and motion control. Medical. Advanced sophisticated instruments are being developed for data recording and physiological analysis. Some of the medical devices and equipment used are stethoscope, respiration monitors, defibrillator, glucose meter, and pacemaker. Defense and aerospace. Defense and aeronautical applications include missile launching systems, rocket launchers for space, aircraft systems, cockpit controllers, boom barrier for military applications. Cathode ray oscilloscope. Thermiotic emissions is the process of emission of electrons from a heated metal surface. How does thermiotic emissions occur? At room temperature, the electrons are free to move but remain inside the metal. If the metal is heated at a high temperature, some of the free electrons may gain sufficient energy to escape from the metal. Cathode rays and properties of cathode rays. Cathode rays. Thermiotic emissions can be used to produce a continuous flow of electrons in a cathode ray tube. When the cathode is connected by the anode by an extra high tension voltage supply, a narrow beam of fast electrons will move to the beam of electrons moving from the cathode to the anode is called cathode rays. Properties of cathode rays. Negatively charged particles called electrons. Deflected by electric and magnetic fields, traveled in straight lines and cast sharp shadows, travel at very high speeds and have kinetic energy, can cause fluorescence, a process where the kinetic energy of the electrons is converted into light energy. Cathode ray oscilloscope. It converts electronics and electrical signals to a visual display. The cathode ray oscilloscope CRO consists of the following components. Electron guns. The electron gun is used to produce a narrow beam of electrons. First filament. It's heated when current flows through it. It is used to heat up the cathode. Second cathode. Heated cathode emits electrons through the process of thermiotic emissions. Third control grid. Controls the number of electrons in the electron beams. Fourth, focusing. To focus the electrons into a beam and anode to attract the electrons from the area of the control grid. And finally, accelerating. To accelerate the electron beam anode towards the screen. The deflection system allows the electron beam to be deflected from a straight line path when it leaves the electron gun. Y plates is to move the electron beam vertically up and down the screen when an input voltage is applied across it. The function of the X plates is to sweep the electron beam across the screen horizontally from left to right at a steady speed. From figure 1, we can say no input voltage. The electron beam does not deflect and the bright spot is at the center. From figure 2, positive voltage is applied. The electron beam deflected upwards. The bright spot moves to the top. From figure 3, negative voltage is applied. The electron beam deflects downwards. The bright spot moves to the bottom. From the last figure, the AC voltage is applied. The electron beam deflects up and down. the bright spot moves up and down to form a bright vertical trace on the screen. The fluorescent screen is coated on the inside surface with some fluorescent material such as phosphor or zinc sulfide. When the electron beam strikes the screen, the material starts to glow. This enables a bright spot to appear whenever an electron beam strikes the screen. The working principle of the cathode ray oscilloscope, CRO. Focus. Control the sharpness of the bright spot. Connected to the focusing anode. Brightness. To control brightness or intensity of the bright spot. Connected to the control grid. X shift. To adjust the horizontal position of the bright spot on the screen. Connected to the X plates. Y shift. To adjust the vertical position of the bright spot. Connected to the Y plates. Y gain. To control the magnitude of the vertical deflection of the bright spot. Connected to the Y plates. Time-based. To control the magnitude of the horizontal deflection of the bright spot. Connected to the X plates. Power switch. Control the power supply. X input. A terminal to connect the voltage to the X plates. Y input. A terminal to connect the voltage to the Y plates. Earth. To disconnect the input voltage at the Y plates and to earth the input terminal. AC-DC switch. To select the type of input received. The display wave. It is measuring voltage from the DC source using a CRO. The potential difference. DC voltage is equal to displacement of the bright spot from the zero position multiplied by the selected range of the Y gain control, equals to number of division multiplied by V over div, equal to 4 div multiplied by 1V over div, which is equal to 4 volts. If the time base is switched on, a horizontal trace is seen across the screen. The values of the DC voltages are the same. This causes the bright spot to fly up and down at a high speed between its positive and negative peak values, tracing out a vertical line. Short time interval. The time base is set to 1 millisecond per division. It means 1 div is equal to 0.001 seconds. The number of divisions is counted between two crests of a wave. The short time interval between pulses is equal to multiplying the number of division by the time base. Semiconductor diodes. Semiconductors. A material that has an electrical conductivity that is between that of a conductor and an insulator. At 0 Kelvin, it behaves as an insulator. When the temperature increases, the conductivity of the electricity will increase because its resistance will be lowered. N-type and P-type semiconductors. N-type is to produce an abundance of the electrons in the semiconductor. A silicon atom has 4 valence electrons. If atoms with 5 valence electrons, pentavalent atoms, are doped into the pure semiconductor, then each of the pentavalent atoms will have 4 covalent bonds and 1 extra electron. Each of the pentavalent atoms donate an extra electron is therefore called the donor atom. P-type is to create an abundance of holes in the material. If atoms of 3 valence electrons, trivalent atoms, are doped into the pure semiconductors, 1 electron is missing from one of the 4 covalent bonds. The deficiencies of the valence electrons are called holes. Since the trivalent atoms accept an electron, it is therefore called the acceptor atom. Semiconductor diodes is a device that allows current to flow in one direction only, but blocks it in the opposite direction. A p-n junction is formed when an n-type and p-type semiconductors are joined together. The boundary between the p-type and n-type regions are called the junction. At the p-n junction, electrons from the n side move to the p side and recombine with the holes. Depletion layer. The region around the junction is left with neither holes nor free electrons. This layer, which has no charge carrier, is a poor conductor of electricity. Function of diodes. Forward bias. The p-type of the diode is connected to the positive terminal, and the n-type is connected to the negative terminal of a battery. The diode conducts current because the holes from the p-type material and the electrons from the n-type material are able to cross over the junction. A light bulb would light up. Reversed bias. The n-type is connected to the positive terminal, and the p-type is connected to the negative terminal of the battery. The reverse polarity causes a small current to flow as both electrons and the holes are pulled away from the junction. When the potential difference due to the wide depletion region equals the voltage of the battery, the current will cease. Therefore, the bulb will not light up. Diodes as rectifiers. Converts alternating current AC to direct current DC. Rectification. A process of converting AC into DC by using a diode. There are two types. First, half-wave rectification. Second, full-wave rectification. Half-wave rectification. When a diode is connected in series with the resistor, any current that passes through the resistor must also pass through the diode. Since diodes can only allow current to flow in one direction, therefore the current will only flow in the first half cycle when the diode is in forward bias. The current is blocked in the second half cycle when the diode is in the reverse bias. Full wave rectification. A process where both halves of every cycle of an alternating current is made to flow in the same direction. This lesson will be continued in part 2. Thank you for listening.